So next presentation is given by Professor Fruits Banush. The presentation title is Understanding the Hydrogen Embrittlement by Novel Critical Experiments. So please start.
Thank you very much for introduction, and I would also like to thank the organizer for giving me this chance to be here and present our results on hydrogen embrittlement. I would also like to acknowledge PhD students who have been working on this topic. Yun Deng, Shu Lu, Yaninge doing the modeling with the discrete dislocation, the Dong, and also postdocs Talon and Bjorn, who has been working on the topic, and the results that I'm showing are made available by their works indeed. Okay, but let's take a look at hydrogen embrittlement first and see how it manifests itself. This is a test done on a TWIP still that we kindly received from Aachen. And then we charged the same sample with hydrogen and tested it in SEM with hydrogen. And that's what we see, in fact. And if you just remember the previous talk also, you can see that typically hydrogen embrittlement is manifesting itself as a kind of reduction in the ductility and deformation. And when you're looking further, you see that in fact what's happening are these incidents, localized deformation, crack formations, which has been distributed in space and time on the surface when they are happening. So it seems like that when at different positions, at different position in a sample, we are reaching to a certain amount of the concentration of the hydrogen and certain amount of the deformation, something's happening, and these incidents which are related to the hydrogen effect on material properties are coming into action and just making strain localization, sometimes forming cracks, and that ends up as a hydrogen embrittlement. So therefore, what we are thinking, here also is another picture from the same alloy that has been deformed for the exactly same amount of the deformation. So 20% strain, this is without hydrogen, this is with hydrogen. So you see these are the kernel average misorientation maps, and you see a very uniform deformation here, but while here we have a very ununiform deformation and formation of these cracks at different location at the grain boundaries, for example. So, but this is only, I showed these results only to motivate and say that if we want to understand the hydrogen embrittlement, maybe we have to also look at the hydrogen embrittlement from the other side of the length scale, so and looking at the smaller scale and see how hydrogen and plasticity are interacting with each other. So to realize this, almost 12 years ago, I started to do nano indentation inside electrochemical cell with hydrogen charging, and specifically we focus on this popping phenomena, which is related to the dislocation nucleation in the material. So to realize this, we had an electrochemical cell where we were able to charge hydrogen and then do the nano indentation and observe the effect of the hydrogen on dislocation nucleation. Typically, we observe this kind of results for a lot of different alloys and metals. This is, for example, is an iron silicon, iron 3% silicon, ferritic steel, and you can see here the black curves are indentation in air, surface topography and indents and the quality of surface, and then we switch to minus 1000 millivolt cathodic polarization, charging, the popping drops, increasing the polarization, popping goes lower, then switching back to anodic polarization and trying to oxidize the hydrogen which has been absorbed into the material, and it goes back to the same amount. These are these green curves that you can see here. And the surface quality, you see nothing's happening on the surface. Everything is related to the hydrogen which is going, or at least we are assuming that everything is related to the hydrogen going into the metal during the hydrogen charging. So based on these experiments, we come up with the idea, okay, hydrogen make nucleation of the hydrogen, formation of the hydrogen easier. And that can be explained also by diffactant concept and hydrogen segregation on the dislocation line, reducing the line energy. But I'm not going to that details. After this, we started to also develop a new approach to study the hydrogen at a smaller scale. And for this, we use a focused ion beam, and we cut this kind of cantilevers in a different materials, and we started to test this cantilever inside our electrolytic cell with the nano indenter in the same manner that we did the nano indentation. So what we did was, again, charging those cantilevers with hydrogen and bending them inside SEM, inside electrolyte, sorry. Typically, the results that we observed was like this. These are cantilevers bended. The material is, again, the same material that we did the nano indentation on that, iron 3% silicon. And the black curves is without hydrogen, and the red one is the sample which has been charged with hydrogen. So in line with what we observed in the nano indentation data, we see a kind of softening, which, again, if you assume that that dislocation has to nucleate on the surface and move to the natural zone of the cantilever to accommodate the plasticity, and you have hydrogen on the surface, which can ease this nucleation of the dislocation, you can explain, okay, this softening can be the result of hydrogen effect in the material. At the same time, this is a BCC metal. We are dealing with the mobility of the screw dislocation. In the same manner, we can explain, okay, double kink nucleation is become easier in presence of the hydrogen, and mobility of the screw dislocation can be enhanced. But interesting things happens when we are adding a notch to those cantilevers. And these are the results of the notch cantilevers, same material, and the black one without hydrogen, and the blue and red one when we charge them with the hydrogen. And then when we look at the notch without hydrogen, that's what we see, and with hydrogen, that's what we are looking. So the process is changing when we are adding notch and a stress concentration, which is, for us, is very interesting, and we think that's play a crucial role here. So to explain it further, we also did test inside SEM. So we have an environmental SEM where we can charge cantilevers inside SEM and watch the process of the cracking while the crack is forming at the root of the notch. So this is in vacuum without hydrogen. This is the second set of bending. So it has been bended once, and then we're bending it, because at the first bending set, there was no crack formation, but in the second run, we were able to see the evolution of a crack at the notch and its propagation. With hydrogen, of course, imaging quality is not that good, so I would like you to just focus on this tiny little rectangular here, where the crack is focused on and shows the process now in presence of the hydrogen. A very sharp crack starts to go. You see the load displacement curve also dropping down. By this kind of test, we were able to measure the crack tip opening distance and also try to calculate the J integral from the effect of the hydrogen, but I'm not going to focus on those things. What I want to mostly show you is the post-mortem analysis that we did on these cantilevers. So these are the load displacement. You see that bending in vacuum, bending in 450 Pascal of hydrogen, and then here also 900 Pascal, and then how it has been affected by the hydrogen effect. And these are the cantilevers. So in vacuum and inside atmosphere or hydrogen, and then you see the fracture of the cantilever. So what we did, we extracted these cantilevers out of the material by the FIP, and then we thin them and take them to the transmission electron microscope or transmission Kikuchi diffraction analysis, and try to study the plasticity around these cracks. If you remember, we see that hydrogen affecting the dislocation, so we wanted to learn what's happening here when we have the notch and the cracking, and that's the outcome of our observation. So what you see here is the curve of the hydrogen charge and hydrogen-free cantilevers, the crack which has been formed inside the hydrogen and the crack in the vacuum. And these are the TKD maps, which has been analyzed by kernel average misorientation again. So it gives you an impression of the amount of the plasticity in vicinity of the crack. So the vacuum, you see a lot of plasticity which has been expanded and extended from the crack tip, and while in the hydrogen you see a very tiny layer of plastic deformation in the vicinity of the crack. The same thing has been confirmed also by transmission electron microscope. You see in the transmission electron microscope a dark layer around the crack where we have a high dislocation density, while in the crack which has been deformed inside the in vacuum without hydrogen, we had so much dislocation that we were not able to locate single dislocation. So the plastic deformation was extreme here. So we said, okay, how we can explain these results? We have the Hirsch and Roberts model for ductile to brittle transition in a crack, which has been proposed typically for BCC metals, where by temperature the ductile crack switches to the brittle by lowering the temperature, and has been based on the nucleation of the dislocation at the crack tip and their mobility away from the crack tip. So we thought maybe the same process can explain what we are observing. If you remember, our nanoindentation data shows that the nucleation become easier. So we can assume in the presence of the hydrogen, nucleation could be easier at the crack tip, but our observation of the plastic region around the crack shows that the plasticity is localized around the crack. So we can assume that this dislocation which has been formed at the crack tip are not able to move away from the crack and shield the stress state at the crack tip, and then the local stress intensity at the crack tip increases, and then we have a brittle fracture. So to also prove this, we started to do a simple discrete dislocation dynamic, two-dimensional discrete dislocation dynamic simulation by using a model which has been provided by Alexander Hartmeier from Bochum. So the typical thing is that we are building such a crack with the sources defined at the specific slip line, so dislocation nucleates and move away. So we are applying a load on crack, check for dislocation nucleation, calculate forces on those dislocation, let the dislocation move and shield the stress at the crack tip, and then again we check if we are reaching to a certain amount of the stress intensity, which can result into the fracture. So again, to explain what is that, how it's related to the two-dimensional model that explain the things at the crack tip, this is the two-dimensional model, and if you assume that dislocations are meeting, we can assume that considering one line here is a very good representative, this two-dimensional model is a very good representative of the three-dimensional process happening there. So these are the results of typical results of the changes in the local crack tip stress intensity versus applied stress intensity. So you see here by nucleation of the dislocation, the stress intensity drops, and by each nucleation and movement of the dislocations, the stress is shielded by the dislocations, and the applied stress is far larger than the critical stress for the fracture. And as soon as we are reaching to this limit, we can assume that the fracture happens. So we are using this mobility law for a dislocation movement. This is based on the nucleation of the double kinks. So we have a thermally activated component and the activation volume for the movement for the formation of the double kink. So these are the results of our simulation and how we are changing some parameters to get different responses. So the gray distribution is the distribution of the dislocations from the crack tip in normal values that typically has been used for this kind of simulation. And then we are changing the typical values which are related to the movement of the dislocation here. So we are changing the activation volume for double kink nucleation, and what we observe that the mobility is dropping, dislocations are not able to move away from crack that much, and we have a drop in the stress, applied stress intensity. We change the activation energy for formation of the double kink, and we increasing it as a result of the presence of the hydrogen, and again we see that the dislocations are accumulated closer to the tip. In order to change the nucleation criteria, we use a simple change in the strength of the dislocation by reducing the Berger's vectors, and what we see a larger amount of the dislocation closer to the tip, but not too much effect on their mobility. And when we sum up all these changes, what we observe is a accumulation of the dislocation very close to the tip, and this is in very good agreement with what we are also observing when we have the hydrogen. The dislocations are just remaining very close to the crack tip, and as a result of that we have a drop in the applied stress intensity and reduction in the ductility of the material. So by this I would like to summarize. So our observation shows that hydrogen embrittlement on the macro scale is a result of local temporal incidents, especially distributed in the macrostructure. So in order to understand what's happening, it's necessary to look at a smaller scale and try to localize these incidents. So to realize this, we use nano indentation, we use microcantilever with notch, and studied the crack initiation in this ductile material. Post-mortem analysis showed that the plasticity has been influenced by hydrogen and it has been localized, and then we made this two-dimensional discrete dislocation dynamic modeling, and by varying the mobility of the dislocation as a result of the presence of the hydrogen, we were able to simulate the similar condition here. So the take-home message would be, at least in our case, what we are observing is that presence of the hydrogen at the strain area of the crack tip results in the local accumulation of the large amount of the hydrogen there, which this hydrogen interact with the plasticity at the crack tip, pins the dislocation, acts on the mobility, and by this, the shielding effect of the dislocation is shut off, and then we reach quicker to higher stress intensities and the cracking process happening. So I would also like to acknowledge Research Council of Norway for the support through for the micro nanofabrication facilities, NURFAB, HIP, and HyFlex project, Max Planck Institute, Aachen, and also University of Bochum. And thank you for your attention.
So we have time for one question.
We specifically cut them on a right, I would say, on a fracture system which is kind of symmetric. And if I go back to that picture there.
You expect to be able to get slip in both directions.
Yeah, exactly. Because, yeah, here, if you look at this, I mean, this is the surface normal and this is the axis normal. So you are expecting that you activated two slip systems here, and then we pay a specific attention to that. So every immerse dislocation.
Geometry that actually suppresses opening.
Exactly.
And so you keep increasing the load,
Yeah.
but you're shielding emission and you're shielding opening. And those two will never cross, so it should never fracture. In the mall.
Yeah, in the mall.
Evidently the experiment does.
In presence of the hydrogen.
Yeah. Well.
So anyway, let's thank the speaker.